You know, it's been almost 200 years now since that famous night when Paul Revere looked up into the church tower there in Boston and saw the lantern which signaled to him the approach of the enemy. Now, in the period of time since then, there have been a great many changes, but the one change that has been most important to all of us is the fact that today our two oceans, one on either side of the country, are no longer barriers to a sudden surprise attack. Now, let's watch this. Now, this is an enemy bomber. Now, what we saw there could happen to any of us. Fortunately, it is the responsibility of the United States Air Force to prevent such disasters. The old lantern of Paul Revere's time has given way today to such modern things as the electronic eye, which sweeps the sky both by day and by night to prevent the arrival of any unwelcome intruder. So let's look now at our all-important radar defense screen. To tell us of this, we are privileged to have as our guest on Science in Action, Brigadier General James W. Andrew, United States Air Force. Welcome to Science in Action, General Andrew.
Thank you, Dr. Harrell. I'm glad to be here. I'd like to point out that while the Air Force is responsible for air defense, we are closely assisted by a group from the Army and Navy, as well as a very important group of civilians known as the Ground Observer Corps.
Well, in looking at this map over here, I can see that it must take a tremendous group in order to do all of the things that you have to do. We have some 3 million square miles of territory here in the United States, and just about 10,000 miles of both border and coastline completely around the country.
It's such a big job, Earl, that the Air Force has made the Air Defense Command a major command of the Air Force, with headquarters in Colorado Springs here, headed by a 4-star general, Benjamin W. Chidlaw. He has his command divided into 3 air defense forces. The Eastern Air Defense Force, made up of 3 air divisions, the Central Air Defense Force, made up of 5 air divisions, and the Western Air Defense Force, made up of 3 air divisions. This area is covered by a network of radar stations with overlapping areas, something like this.
In other words, then, if one of these radar stations should go out, then the radar station on either side could cover that area without any trouble.
That's right.
Well, I know that your command headquarters are right here at Hamilton Field, and when I look over to this relief map, I find that Hamilton Field would be just about at this point right here. Not so far away, up on the top of Mount Tamalpais, is a very strange-looking ball. Now, I know a lot of people have seen that, and perhaps have seen other things in other parts of the country that look like it. Now, what is it, and what does it do?
I'd be glad to talk to you about that, Earl. If we'll come over here to this model, I think I can show you a little better what it is. This bubble, which you spoke about, simply covers the antenna of our radar station. Primarily, it's a protection against the weather. We can't cover this antenna with metal, nor even with material like wood, which would be held together with metal or with nails, because the metal would interfere with the radar signal. So this radome, as it's called, is made of nylon reinforced rubber, which is very strong. It's inflated by compressed air, just like a balloon.
Well, since this bubble is a sort of a raincoat, then let's take off the raincoat and see what's on the inside, the important part of the insulation. Here, of course, we see the antenna. But before we examine this in detail, perhaps we should find out just what radar is. You know, since World War II, radar has become a household word, but it's still somewhat mysterious.
Well, radar is a coined word, Earl, and I could explain it simply like this. RA stands for radio, D for direction, A for and R for range. Radio, direction, and range. It's simply a method of using electromagnetic waves to detect the presence of objects which are beyond our normal vision.
Well, now, these electromagnetic waves that you speak of, those are the same waves that we use in radio and also in television, but here in radar, you use them for a different purpose.
That's right. Radar seems mysterious because we can't actually see the waves, but we can demonstrate the principle rather easily by using water. If I drop a pebble like this, you'll notice that it starts a series of ripples that move out toward the edge in circles. When they hit an obstruction at the edge, they start coming back toward the point where we drop the pebble.
Then in radar, the transmitter would correspond to that same pebble, and as it sends out its radio waves, the waves that hit an obstruction, they bounce back and be reflected back to the radar station again.
Yes, and since our radio wave travels at the speed of light, which is 186,000 miles per second, the echo from an object 200 miles away would come back almost instantaneously. In fact, we have to measure the time in microseconds. This insulation here contains both the transmitting and receiving antenna for a radar station.
Well, you know, it looks somewhat like a dish or one of these futuristic things we see. It doesn't work that way, of course.
Well, not exactly, but it's somewhat similar. I'd say that this dish-appearing affair acts somewhat like a mirror. The radio energy is transmitted up through this little horn right here. It's reflected back onto the antenna or mirror, concentrated and sent out into space. Now, if in this concentrated area it should intercept a mountain, a ship, or an airplane, it will be reflected back onto the antenna, be picked up in a sort of reverse direction.
Well, now, I just plugged this in, and of course we can see it moving around, and over here we have two aircraft. Here's an interceptor here. Here is an enemy aircraft, and notice each of them has a small light underneath, and as the radar antenna comes over, it turns on this light. But then we have something else happening down here, and what happens here, General?
Well, I think this Bendix model here gives a very good illustration of the way we intercept an unknown aircraft, Earl. As the antenna goes around, this beam of energy, which I spoke of, is thrown out into space, and as it intercepts the hypothetical bomber track, it sets up a little blip of light right there. Now we have here an interceptor on its way out to intercept this hypothetical bomber, and as the antenna goes around, it makes this little beam of light right here. Now, the radar operator will be sitting in the middle of his scope, right about that point right there.
In other words, this sweep hand, as it moves around then, would leave these marks as we see.
That's right. He has a series of concentric circles, something like this, by which he can measure the distance which the blips are away. And as this hand, this sweep, goes around, these spots of light are illuminated as you saw.
Well, that's a very simple demonstration or an explanation for a complicated piece of equipment. We have one of these over here now, and I see the operator is just warming it up. There are all sorts of dials and gadgets there and everything else. And before we actually turn that on, perhaps we could look again, General, at a photograph of what the sweep hand's going to do now as we see it moving very shortly.
Well, yes, this shows it very well. Here is an illustration of the sweep hand, which I spoke of here, corresponding to the line which I drew on the radar scope. Here you see the little blips of light which correspond to the concentric circles in this manner. Here you have a rather large blip of light which would show a radar track. That large spot is probably a bomber or a group of smaller planes. Here you see another bright spot, which is probably an interceptor such as this going out to intercept the bomber.
Well, I can see here that the signal is starting, and then as it starts in, the hand begins to swing around, and very shortly, as it moves around, those little bits of light that you mentioned come into place. There are two planes approaching each other, one from the east and one from the west.
You can see the blips are getting closer together. Since we can figure the distance the plane has traveled in a given length of time, we can also determine his speed. Then, by utilizing another antenna, we are able to determine his altitude. By this time, a plotter would be able to start plotting the course of these planes on his board.
Well, now, this plotting board that we have here in the laboratory, I understand is very similar to those that you have at various radar sites in the Air Defense Network. And, of course, as you mentioned, the purpose is to correlate all the information you get on each plane in flight.
Roger.
Incidentally, I notice your man there has to write backwards, and what amazes me is that he can write backwards and do it very quickly.
He has to be able to do it fast. Those planes really move. Our two planes are coming right along. I think we might take another look at our screen.
Roger.
You see how the flashes are coming very close together. Our interceptor to the right is getting close to the unknown. Now they're almost touching. At this point, if the plane was friendly but unidentified, the interceptors would send back an identification.
You have two types of grids there. In other words, starting from the point where he would be located in the center, you have a series of circles, and then over that you have superimposed a number of squares. Now, just what does that mean, and how significant is it?
The radar operator represents the hub of these concentric circles.
Right.
When he calls out the range and direction of a plane on a scope, he's speaking of it in relation to his own position. But if I'm trying to follow the course down here at Hamilton Field, it wouldn't mean a thing to me.
In other words, it'd be like somebody in the next laboratory saying, well, now, where are you, General? And you would answer him, well, I'm standing 1 foot to the right of me. You wouldn't know where either one of us were.
That's exactly right. So we have this circular diagram, or polar grid, which I wanted to point out and did point out a while ago. These concentric circles which give distance. But over that, we can place a geographical grid, something like this, which by which we can tell the exact position of a plane regardless, because these are measured in latitude and longitude.
And one of these squares will always be the same no matter where you are any place in the world.
That's right.
You can always find it. Well, let's go now to a typical radar center or a direction center and see the type of work that is carried on there. Now, I see the huge plotting board, very much like the one that we have here, and I notice that there are a number of scopes there. Those have different sectors, do they?
That's right. You'll notice the two men down at the table, down in front. They are the tellers who are in direct communication with the control center at the airfield.
And the men in the back, then, would be they would be responsible.
Those are plotters.
Carry
Yes,
on
sir.
the work there.
Yes, sir. Those are the tellers there.
Well, now, I can see how you could correlate all that work there, but let's look at this map over here, because here's something I'm not clear on. In other words, you could tell a plane and identify it in the continental United States, but what if you had a plane out here in the middle of the ocean? What would you do then?
That'd be no problem at all. To save money, we've set up what we call a corridor system, something like this, with 5 corridors. That's a little larger than it actually is, something like that. Now, the Civil Aeronautics Administration has set up a system whereby they give each pilot who leaves Honolulu a sealed envelope. And in that envelope is a set of instructions which he must follow very closely, because if he gets in the wrong corridor here and follows the wrong instructions when he opens his envelope, we send an interceptor out to determine who he is.
And if he's all right, then you let him come in. But if it happened to be somebody else, why, then the interceptor would be able to tell about that.
That's right. Usually they're in the right corridor. We've saved about $30,000 a month since we've set in that system, because interception is really an expensive process.
Well, I know that in your control center, these little raid stands, as you call them, are vitally important. They're rather complicated, so I wonder if you could perhaps set up one of these here and give us an idea as to what these various markings mean.
I'd be mighty glad to do that, Earl. I'll make up a raid stand for you. Here's the top block, which is the identification of the aircraft. Now, this happens to be a yellow block, which would indicate that he's unknown. We have green blocks for friendly and red for hostile. Fortunately, we've never had to use any of those. The second block, which I'm going to put on the raid stand, is the identifier of the radar station, which is carrying the track. That is the first one
which picked it up originally.
That picked it up, the first one which picked up the track. Now, each radar station gives a track number, so this first station gives the track number 15. That means that in the last 24 hours he's picked up 15 tracks, and this is the 15th track. Now, the next block is the designator of the radar station, which is presently carrying the track.
In other words, it's moved away from the first radar station, and now another station has picked it up.
You see, a plane can be flying along the coast, it'd be picked up by a station, and is carried by a secondary station. Now, here we have the block which indicates the number of aircraft in the blip. Then we have its altitude in multiples of thousands. This would indicate 20,000 feet. And there we have its speed, 259.